probability mass function, which is the probability that a random variable x is going to take on a given value small x. So it's just the values of the probabilities over some given values, and then we combine it to form a function called probability mass function. So we're going to illustrate this concept with an example, which is the transmission errors. So when we transmit data from one point to the other uh, for some, in real scenarios, there are errors that occur during the transmission of the data. So we look at this example, transmission errors. So in this case, for a binary communication channel, we get bit errors with some certain probability. So let's say for this example, we use the random variable x, which is, for this particular problem, is the number of errors, number of bit errors. You can say the number of errors in n number of independent transmitters. So basically, we send n pieces of information or n bits of data, and in those n number of independent transmissions, we look at how many times the data gets corrupted or there are errors in the transmission. So we just track the number of errors in this n independent transmission. So the objective is, there are two objectives. Number one, we find the PMF, probability mass function, for this random variable x, which is defined as the number of errors in independent universals. And number two, we also want to find the probability of one or fewer errors in the above scenario. So what's the probability that there is only one error or a few errors, which obviously is zero errors. So if we are working with a discrete number. So here you can see that x is actually the number of errors. So we can have, absolutely no error, which in an ideal case we can have zero error. So x could be equal to 0. X could be equal to 1, in which case we can only get one error in the transmission. Or we can, in the worst case, we can have all the transmissions, getting corrupted, and we can in the worst case we can have n number of errors. So in the best possible case, on one hand we can have zero error, no transmission error, and in the worst possible case we can have n number of errors for the given scenario. So the sample space Sx, which is denoted by Sx, the sample space is going to be a discrete set of 0, 1 up to n. So 0 means no error, 1 means single error, 2 means 2 errors, all the way up to n. Now, we are also given that for any bit error, the probability of a single error is given as p. It's actually small p. So small p denotes the probability of a bit error. So let's say we can say that we can just assume if there is no error for a given transmission, we denote it by 0. And if there is an error, we can denote it by 1. So according to our notation, we can say that the probability of an error, which we denoted by 1, equals small p, whereas probability of no error, which we denote by 0, is actually equal to 1 minus p. So remember, it is not x, it's not the value of the random variable x, which is defined as a number of errors. So we can have a string of these numbers such as 1 1 0 0 1 1 0. So in this case, we can say that there are 4 errors. So x is equal to 4 for this case. So 4 errors for the above case. Now I want to find, first of all, I would like to have the PMF, the PMF of x. So the for the PMF, I want to look at what is the probability of k number of errors in n bit transmission. Now k could be 0, k could be 1, 2, all the way up to n. So what I'm equivalently saying here is I want to find the probability of an error pattern where we have k errors, where we have k number of ones and n minus k number of zeros. So we have n minus k of zeros, right? So for that, the PMF is going to be equal to Px k, which means x is equal to k, probability that capital X equals k number of errors, and obviously it's going to be given by the nck times p raised to power k times 1 minus p raised to power n minus k, where k goes from 0, 1 up to n. Call it equation number 1. So this is the PMF. This is the PMF of our case. Now the second part says, now obviously this x is also called, this x is my random variable, and it's called binomial random variable with parameters n and p. So, so whenever you want to specify a binomial random variable, you mention two parameters: the number of transmissions or number of trials, number of experiments, which is denoted by n, and the second parameter is the probability of each experiment's success or failure. So we specify it with P. So we could be looking for success of an experiment, we could be looking at the failure of a certain experiment. So it just depends on the problem. So here in this case, we are looking at the number of errors. So we specify the probability of each bit to have an error by this um, P. Now the next part of the question is to find the probability that this x is equal to or less than 1, which means either there is absolutely no error, in which case k is equal to 0, and this is p raised to power 0 and 1 minus p raised to power n plus and 1 p raised to power 1 and 1 minus p raised to power n minus 1. So this goes as, well, this is 1 minus p raised to power n plus n times p into 1 minus p raised to power minus 1. This is the probability of having one or fewer errors in n number of transmissions. So this is how we can find the probability from the given mass function Pmf, which we derived in the previous line. So that's all from the from my side.